From the primordial cloud of gas and cosmic dust, gravity forged the stars. Gravity connects star systems together in vast galaxies and steers them on their journey through unbounded space. The relentless flow of time has driven the evolution of the universe and created extraordinary wonders. Some galaxies form so close together that they're locked in a gravitational embrace. What a magnificent sight it would be. As it evolves, the universe passes through distinct eras. Vast ages whose beginnings and endings are marked by unique milestones. The births and deaths of its wonders.
We are the product of a grand evolutionary sequence, cosmic evolution, about which we are only occasionally aware.
Gravity is the great creator, the constructor of worlds. But gravity is also the destroyer, because it's relentless. When a star around 15 times the mass of our Sun collapses, all the matter in its core is crushed into an infinite void of blackness known as a stellar mass black hole. The immense gravitational pull of these monsters can rip a star apart. They tear matter from its surface and drag it into orbit. This superheated matter spins around the mouth of the black hole, and great jets of radiation fire from the core. Although these jets can be seen across the cosmos, the core itself remains a mystery. Not even light can escape, so their interior is forever hidden from us. Throughout a star's life, there is a constant battle between energy pushing out and gravity pushing in. When it runs out of fuel, the star collapses and then explodes with the brightness of 1 billion suns. As the star is torn apart, it will fire out out into space all the elements that it created in its life and death. These are new stars forming from the elements blown out by supernova explosions. New stars being born from the remains of dead ones. And it's from this universal process of death and rebirth that we emerged. Because it was in a nebula just like this, 5 billion years ago, that our sun was formed. Clouds of hydrogen collapse further and further under the force of gravity, and the life cycle of a new star has begun. A star was born that would come to be known as the Sun. Around it, a network of planets formed. Among them was the Earth. Debris left over from the formation of the solar system collides with the Earth. Earth began life as a molten hell.
The early continents were still forming. The land was dominated by volcanoes, hostile and lifeless. But deep in the oceans, life had begun. The latest theory is that chemicals spewing from underwater volcanic vents solidified and created the conditions needed for the first cells to form. For some 3 billion years, simple microscopic organisms were the most advanced form of life on the planet. Cyanobacteria and other oxygen-producing microbes began to bloom. These flourished in colonies of plant-like microbes that pumped out enormous volumes of oxygen. And it was this increase in oxygen that was the key to the rise of the animal kingdom.
Organisms started using oxygen to respire, yielding a lot more energy, which allowed the development of more complex life.
Just before complex life appeared, the world was in the grip of the biggest ice age in its entire history. And then suddenly, advanced organisms appeared.
Well, that was an amazing video on something that interests all of us. Like, I'm pretty sure that video represented something that most of us are interested in. Who doesn't love something curious, right? The stars, the galaxy, they indeed create a vast curiosity among those of us who are at constant seek for truth. If you're someone with questions about what is hard to reach, what is hard to see, then you are at the right place. So, well, a very good evening to everybody here. So, with us, we have a guest speaker today who is a passionate amateur astronomer. She is someone with immense curiosity, enthusiasm, and interest for the space, and she is indeedly in love with astronomy. So we have here with us today Miss Malmi Kiriwandalage, an astronomy and planetary science research student at Stony Brook University, New York. She is also a NASA JPL Solar System Ambassador. Miss Malmi, we warmly welcome you to our Life in the Universe Astrobiology webinar. We are looking forward for an indicating evening. So the stage is yours.
Hello, everyone. Thank you so much for the introduction. Thank you for inviting me. First of all, you guys can see me. Can you hear me? Yeah?
Yes, it's
Okay.
pretty clear.
Awesome. Thanks a lot again for that amazing introduction. I appreciate it. And first of all, thank you for everyone who joined today's talk. And thank you, Pasindu and his team for inviting me. This is amazing, and I'm really glad you guys are here to talk, to understand the astrobiology. Yes, as it says on the topic, I will be talking about the life in the universe, which is understanding the subject of astrobiology. All right. So without going any further, actually, let me give a quick introduction about myself a little bit further, so you know where I'm, who I am, and what I do. Just as she said, I do have affiliation with NASA, but I'm also a research student, and originally I was born and raised in Sri Lanka, and I came to US about 9 years ago. So if everybody could do me a favor, and if you could mute yourselves so we don't have any distractions, and you guys, if you have any questions to maybe during the lecture, you can leave it on the chat group, or you can let me know towards the end. And at the end, for about 15 minutes, I always do this, like I would talk to you guys what I talk, and like sort of like have a discussion and answer the questions. So yeah, so I was I work with the NASA, and I do have affiliation with and such as, but what I'm mostly interested about astrobiology, that's like the most thing I want to do, that because I always curious about what is out there, like why I'm here in this earth, like why I'm not somewhere else. I had all these questions in my mind, and not everybody in Sri Lanka was able to answer my questions, so I had to sort of study by myself. And once I got the opportunity to come here, I knew that I have the advantage of continuing my studies. And that's when I was introduced for astrobiology. I knew about astrobiology, but it's, what funny is, like back in 1970s, that's when like astrobiology was actually introduced to this world, like sort of like another branch of astronomy. So it's pretty new. Okay, it's pretty new. So I didn't know much about it until I come here and I actually study about the biology aspect, geology aspect, astronomy as wise, and then I understood, oh, okay, this is what I want to do. I mean, I wanted to understand what is my origin, why I'm here, and that's the only way the reason, like the only way to find the answer for that is to understand the overall astrobiology. So when I chose this topic, I knew, like, this is like the amazing topic to introduce you to something that I'm passionate about, and something that very new, and more researches has to be done in future. So without further lateness, we will start, and I will share my screen with you. Okay. Let me double check with my hold on. Okay, my thing is here. Awesome. Let me. Okay. Okay. Is this screen available for you guys? It is.
Yes, okay. We can see it.
Oh, okay, good. Awesome. Alrighty. So let's start. How do I slide? Okay, so the life in the universe, understanding astrobiology. You know my name and my affiliations. So, and this is me. This picture was taken at the NASA Jet Propulsion Laboratory in California. Inside the Mission Control Center, I was able to get the access to go visit, and this is like one of the amazing memory of me visiting NASA JPL. And as you can see on the screen, it says Inside. This is like a few months before Inside launch, and NASA was getting ready for launch of Inside, which is understanding the mission to understand the geology of Mars. And I was just taking a pictures. It's like amazing place. This is where like if you see videos of scientists at NASA going, yeah, hooray, and likewise, that's inside this place. Once they launch, this is where they celebrated. So I was very honored to be able to visit inside. Not everybody allowed it, even visitors. So it's pretty amazing. All right, so what is astrobiology? Well, it's start with the life, but even before the life occurred, start with the organic compounds, the gases, the genetics, and then building these basic building blocks. And then from there, the molecules, the microbes, and then planetary systems, exoplanets, exosolar systems, of course, aliens, if it's possible, icy walls as such. So this like the understanding the biology aspect of astronomy is basically astrobiology. It's very simple like that. The definition is simple. But if you understand the deep definition, it's basically astrobiology is study of the origin, evolution, distribution, and future of the life in the universe. And it's include for the life in Earth and life in extraterrestrial life. So that means life outside the Earth. So simply, it's a study of potential of the universe to harbor life beyond the Earth. So it's amazing subject to study. So quick history background. Not only we know about the possibility of life that could exist outside the Earth, there were few philosophers and astronomers back in the Greece. They mentioned about possibility of life. So for example, Epicurus, who is a philosopher, he said there are infinite worlds, both like and unlike this world of ours. We must believe that all the worlds there are living creatures and plants and other things we see in this world. This was like his theory without any evidence, because at the time, obviously, technology was not advanced, and they basically used their own theoretical hypothesis to give a sort of like a evidence or just explain their point of view. So but this is his guess, what he assumed at the time. And then there was a theologian, his name is St. Thomas Aquinas. He's actually a father for one of the church, and which is amazing because usually church had a lot of impacts or in astronomy, like they had arguments, but a father like Thomas Aquinas had a different view. So he said When it is said that many worlds are better than one, this is sort of better. It does not belong to the intention of God, because for the same reason, it could be said that if he made two, it would be better that there were three, and thus it is infinitum, which is why he's questioning, why would God create just one planet? What if he created two? What if he created three? Or what if he created infinite number of planets, just like our Earth? So he was arguing about it. And then there was another philosopher and mathematician. His name is Giordano Bruno. So he is a supporter of Copernican model, which is the model of heliocentric, which is the Earth and other planets revolving around the sun. So he supported that, and then he believed on infinite number of worlds. All these astronomers and philosophers, they wasn't able to provide definite, solid evidence. They were assuming based on their own hypothesis. Okay. So NASA, and including all the other astrobiologists, have these three questions that they always question about. The basic three scientific questions is, number one is, how does life begin and evolve? Number two is, does life exist elsewhere in the universe? Number three, what is the future of life on Earth and beyond? So my presentation is going to be based on these three scientific questions. So the number one, we try to understand the evolution of our Earth, and then how it affected the solar system, and then how we go from there. And then second is about the exoplanets and extrasolar planetary systems. And then number three is how we gonna are we going to go to another planet? Are we going to find a civilization? What is the future that holds for us? Okay, so astrobiology has connected for 5 definite areas. These 5 interconnected areas are part of astrobiology, but it is very as it says on the word astrobiology, biology is in astronomy. So in astrobiology, we do, just like how biologists understand, we understand the diversity of life on modern Earth. That includes the phylogenetic tree, metabolic diversity, and then from there we understand the evolution of the Earth. So starting from microbacterial life, stromatolites, cyanobacteria, and then how the evolution of the gases occurred on Earth. So oxygen, nitrogen, likewise, and then from there we understand the diversity of solar system. So not only Earth, what is other planets in our solar system has, and other moons. So Mars, we believe that it is habitable for us to live. The only one factor that we don't know is about the Mars is based on carbon dioxide gas, which is not good for us. But because all the evidence through the NASA missions and other missions proves that indeed, Mars is habitable, because we see there's a water flow, funnels, tunnels, likewise, and the minerals that gives us the evidence of a past ancient life. And then, of course, Europa, Enceladus, Titan, they are moons of Jupiter and Saturn, and they both, these 2 planets, even though they are not habitable, these moons are actually habitable because they have the water on their surface. And towards the end of this presentation, I will be individually talking about especially Europa, which is one of my favorite topic in astrobiology, and hopefully will be my PhD thesis. I'm hoping, but it's one of the PhD thesis that I'm hoping to work on, and I will be talking about that as well. And then we have planetary environments around this other stars, so habitable zones and exoplanets, which is very important 2 concepts in astrobiology. And of course, finally, the understand the origin of life. So these are the 5 major interconnected areas of astrobiology. All right. Let me go back. Okay. So I'm going to jump right into the habitable zone, because it's very important to understand what is habitable zone is, and why it's important for us to have a life in it. Simply, habitable zone is like the green region of solar system, just like that. And when you try to understand what is green region, it's the green region which has to have the correct air pressure, correct temperature, and correct planetary magnetic field. These three main fields are important in order to have a circumstellar habitable zone, which is we also call as the CHS. So habitable zone is correspond to the range of orbital distance where liquid water can exist on planet's surface. So when I mean by liquid water, a liquid water like our ocean, you know, not the solid water like ice, but actual liquid water. This green region has to have, if the green region is on the area where the planet is, that planet must have a liquid ocean on its surface, which is why when we are looking for exoplanets, we look for a water and we look for possible habitable zones. And so this region around the circumstellar habitable zone it's expand from sun and towards goes towards the like outer area of solar system. So I think I have a slide about the Venus and Earth, but I will talk about that later. It's coming up soon. But this green region is what we really look for when we are looking for a planet, Earth-like planet, so a planet that could sustain a life. So the first main three fields that we are looking is like, of course, the air pressure, because air pressure cannot be too low or too high. This is like basic first law of thermodynamics. So you cannot have a too low pressure, you cannot have a too high pressure. It just has to be the correct air pressure. And then of course, the temperature. The temperature cannot be too high or too low. Because if the temperature is too high, the possibility of life sustaining there is very low. If it's too low, same thing. So, and also planetary magnetic field. The Earth or any Earth-like planets or exoplanets must have to have an atmosphere that protect the planet from solar winds. And without the solar winds, if the solar winds come to the planet's surface, that means the life going to be die from the radioactive energy, right? So the planetary magnetic field has to be able to create the atmosphere that's going to protect the Earth or Earth-like planet. All right. Am I clear so far? Yes?
So far, so good.
Okay, great. Thank you. I might go a little bit fast. It's just I'm so used to talk fast, but you can always let me know if I should slow down. And also my voice is kind of cracking because I've been a little bit sick lately. So if you have a hard time understanding, please feel free to unmute and let me know. Okay. Thank you. All right. So I'm gonna go to the next slide. All right, so this is like the image of habitable zone, that closer view. Just as I told you before, the planet cannot be too close to the sun. That means it's going to be too hot, but it cannot be too far from the sun or the star. It's going to be too cold. It just has to be on this right place, just has to be just right. Okay, so there could be like many 40 billion Earth-sized planets orbiting habitable zones of sun-like stars. So stars that are similar to our sun might have, or actually have, planets like our Earth, and they all are existing in this habitable zone. And these Hubble telescope actually were able to photograph 100 billion galaxies in the universe. And when there are galaxies, there has to have solar systems in it, which means that has to have some kind of planet. So it's just very easy as that. So this diagram shows hotter stars, sun-like stars, which is like our sun, and then cooler stars. So this hotter stars right here, it shows which is the blue giant right here. You can see hotter star means the habitable zone is further from its own star. But sun-like star, like our Earth and our sun, it's just on the right place. If the star is very cold, that means the habitable zone is much closer to the star. That's the picture this image shows. The green line that you see on hotter star, it's very further out from its sun or its star, but sun-like star like our Earth is much just on the right place. It's not too far, not too close. In cooler stars, habitable zone is much close to its parent star or their own sun. So that's the difference between how the habitable zone view on 3 different types of stars. Okay, so I was going to tell you about this earlier. This is what I was talking about Venus. So when our Earth was building up, like during the creation of our Earth, we were not on the habitable zone. The habitable zone actually was in Venus. The Venus was on the habitable zone, but this happened during the beginning of solar system, like towards the first 1 or 2 million years of creation of solar system. The habitable zone was just being towards the Venus, and Venus was actually habitable enough to sustain a life at the time. But within the creation, during the creation, all the impacts occurring, the gravity is too much high, the pressure, the temperature. So habitable zone starts to zoom out from Venus, and it came to Earth. So Earth was able to have a life after habitable zone moved out from Venus. Recently, there was an article about through the some of the astronomers were able to identify that Venus might be able to sustain a life. And this was very debatable back in the days because Venus have a greenhouse runaway effect, which means the gases on Venus is actually based on sulfur, which is poison, right? And it when it's and the gases on the Venus does not go out from its surface or from its atmosphere. It just stay inside it on itself. So like it's like a ball of sulfur dioxide just remain in that planet. So scientists had a lot of arguments, but we were able to actually identify some molecules that are building blocks of life. So we don't know, it might change, but that could be one of the reasons. Could be because Venus used to be under the habitable zone, and now it's finally moving, and it moved out and it came to our Earth. About 2 or 3 years ago, when I was taking my first astrobiology class, I remember we had to calculate the time period of habitable zones. And I had to calculate for the time period of habitable zone for Earth. And I found out, oh my God, the habitable zone of Earth is actually leaving Earth within next 3 or 4 million years. The habitable zone is leaving Earth. And right now, Earth is on the edge, of habitable zone. So about like a month or 2 later, there was an article from International Astronomical Society, and astronomers actually were able to find out that Earth is leaving the habitable zone. Like the habitable zone is leaving the Earth. Like our life is right now in a danger zone like that. So we need to, like, the NASA or any other space agency has to come up with something to go somewhere else. But that's why we are going to Mars, because the habitable zone is actually reaching towards the Mars right now, like it going towards the Mars. So that's a possibility that Mars will be able to become the next Earth. So in that case, we'll known as Martians, not Earthians. So yeah, that's like really a cool thing. But habitable zone is very important concept when it's come to understanding the exoplanetary system or the origin of the life. So it's one of the important concepts in astrobiology. So yeah, this is origin of life, or we call it abiogenesis. So I hope you guys familiar with solar nebula theory. If you're not, it means the how the solar system formed, what formed solar system, such like that. So we all know the picture on my left is like the cloud with dots of stars. This is a nebula. A nebula is like where the creation of life first begin. So it's like the hotter stars or cold stars or just the right stars. They all, along with small planets, they kind of, in the beginning, they kind of live together in a small surface, kind of become like a family, and they kind of crush on its own, just move around. It's like a big giant cloud of hot materials just moving around and forming different things. So our sun was created like that through a nebula. And then this nebula, before the nebula happened, it was actually a star that was exploded through a supernova, and then that supernova remnants are what created this nebula. So this nebula has very close to each other. It's super hot, and it's very tight, and that's when the bigger object kind of attracts the materials around it and sort of becoming to revolve around on its own, creating an attraction like this, and then all the other materials around it start to move around and build their life like that. So that's how the sun and the planets were formed, the solar systems. And these materials like has the evidence of the minerals in rocks. Actually, hold on. I also studied geology, and one of the cool thing about geology is like the rocks can date back to the life, like the formation of the life, or like the beginning of the life on Earth. And this is, can you see this? This is a conglomerate rock. And this rock has the sediments, you can see, it's just collide with each other. And these rocks carries minerals that carries fossils. Fossils are remnants of life that was before us, like, so the bacterial life or stromatolites life or cyanobacteria that we were able to find were actually fossils from these rocks that carries the evidence. Like, let's say in 3 or 4 million years, human civilization is going to die out from the earth. Whatever the leftover human civilization is going to be inside this kind of rock. And this rock is the evidence of there was a human civilization on this earth. And whoever the generation, whoever the civilization that comes after human, going to understand human civilization by looking at these rocks and minerals. It's very important for us as geology, about the rocks and minerals. And one thing about NASA too in Mars is to understand the geology of the Mars, to understand whether there's rocks and minerals. If you keep up with the NASA news, we had a huge mission back in July. It was the Perseverance rover launch. And this rover is going to Jezero crater, which is actually a delta, an ancient delta on the Mars, then possibly have a rock and minerals that probably have water samples and also like molecules actually, and could have some kind of fossils. It's just a hypothesis, but that's what we are looking for. So yeah, minerals and rocks carries a lot of information, and of course. That's other raw materials are gases and molecules, amino acid, not too complicated. Like we all are made of stardust. It's just very easy as it is. The iron in my blood, in your blood, is coming from stardust. The calcium on your bones are coming from stardust. So it's very simple. Like we are just made of stardust. Like when we are looking for, let's say, alien life, we look for alien life that's similar to human life, most likely similar to human life or human, like the gases or molecules that we will build up. So it's very amazing and very cool to understand. Oh my God, we are like, part of this universe, right? Like we are the universe, basically. So I'm sorry, when I get stuck on the presentation slide for so long, let me know. I don't want to waste the time. It's so much fascinating to talk about this stuff. I get lost in my own topics. But yeah, anyway. So hydrothermal vents, this is another, this is important in astrobiology, because hydrothermal vents are what we believe, even biologists believe, that most likely the life was first began. So the hydrothermal vents are a result of seawater percolating down through the fissures in the ocean crust in the vicinity of spreading centers or subduction zones. So let me show you this too. All right, I have 2 highlighters. Okay, so if you don't know what is subduction zone, this is what it is. Let's say this green. Actually, hold on. I should have a blue color one. Okay, there you go. Much easier. Okay, so the green highlighter shows the continental plate continental boundary, plate boundary, and this blue color highlighter shows the oceanic plate boundary. So when two zones, 2 different plate boundaries collide with each other like this, whatever the depth goes down. So we all know the water have a higher density than the land or the soil, right? So water is dense enough to go down like this. It goes inside and creating this crack, this crack. If you can see, this crack is what we call subduction zone. The more denser it is, and this subduction zone, because of the land, so the temperature from the land and the magma and from the down the earth, which is from the ocean, and the cold seawater kind of with the hot magma creates these vents. So this is like the most important concept of how life began, this subduction zone. And around this area is where we found hydrothermal vents, because these vents has a correct temperature, not too hot, not too cold, correct pressure, thermodynamics, not too high pressure, not too low pressure. And this is where the small life forms like cyanobacterials, the stromatolites, these are first began, and these lives formed and evolution happened, and that's how we are here. So, and if you ask me how Earth got water, the answer is from the comet impact. So like we didn't have water when we were first created. We were just a rocky planet, but with the impacts of comets, especially, and then of course the magnetic field was there to create the atmosphere, and then there's the rain, and that's how Earth got water. But the comets are what carries the water, especially. So we know we are actually impacts of comets. That's how the water was created. But yeah, so the subduction zone is where the life was first originated, as the biologists and also astrobiologists believe. So in Europe, which is one of the research that I'm focused on, we know that inside on the surface of Europa, it's actually oceanic crust. I mean, it's a icy crust, but underneath its crust is the ocean, liquid ocean. So when we found about this, we first thought that's the possibility of life in Europa is high, and in order to look for that, we look for hydrothermal vents. Like we could find small crabs, small fishes, jellyfish in Europa. If we can find a hydrothermal vent that possibly able to create the life. So that when we are understanding exoplanets and planets that we possibly could able to sustain a life, we always aiming for ocean or creation of hydrothermal vents. So it's clear, right? So let's go to the next slide. Okay, you guys probably know about the key ingredients of life. So of course it's liquid water, the essential chemicals, which is equal to carbon, hydrogen, nitrogen, oxygen, proteins, nucleic acids, such as, and then energy sources. So energy source means the photosynthesis process, also like the magnetic field also included for this. But photosynthesis is like the energy source because the sun gives us the energy of plants to give us food like that. But there are several other energy sources, like it's include the rain and water in it on the surface in a liquid form as such. But when I mean by energy source, it's sun is like the most important energy source for us. But yeah, the process comes after, which is photosynthesis. So this slide just give like a rough idea of what I've been talking. So we know the universe is 13.8 billion years old, and the sun is 4.6 billion years old, and our Earth is 4.5 billion years old. The same, little bit closer, the same as our sun, but the life on the Earth, which originated about 3.8 billion years ago. So let's start with the sun, creation of the Earth, and the moon collide with us, which is different, separate topic. And the small bacterial life start forming. Then there was the small voluntary and involuntary animals came over, fishes and vertebrate animals, invertebrate animals, and then there was insects, and then evolution, and then finally Homo sapiens. Homo sapiens means us, like humans. So yeah, this is like the short term of life of Earth. And let's go to the next slide. Okay, this just shows like the summary again, but how these are connected to each other. So if we start the origin of life, the bacterial evolution, and just the biology itself is connected to each other. It's just like unending process. So we start with the molecular level, which is gene, protein, and the engineering system. So bacteria, from their environmental level, which is like the rocks, like I just showed you, and then they understand the evolution. So phylogenetics, or understanding through these laboratory experiments and stuff. So these are like the approaches that scientists do in order to understand the origin of life. So they use these fundamental 4 fields of areas to study the origin of life on Earth. And also we use the same concept or same method to identify life in other planets. Okay. All right, so ocean world. This is like amazing topic I want to talk to you. It's like about the Europa, as I mentioned earlier. Ocean worlds are included with the moons are included for ocean worlds as well. When I mean by ocean world, you probably will be like, wait, Europa is a moon, how come we call it a world? But it is a moon, but we use it as the ocean world because it belongs to the group of ocean worlds. So like Europa, Titan, Enceladus, and other ocean worlds, extraplanet ocean worlds are included. Our Earth is ocean world likewise. So alrighty, give me 1 second if you could. I think before I go further, I totally forgot to show you a video that I wanted to show. I should have shown you earlier, but this would be a good time for me to take a break and also for you to watch this video for 1 minute. Let me say, can you all see this? Yeah?
Yes.
Yes.
Okay, awesome. Thank you. Oh, sorry. Okay. All right. Thank you for watching that. It's just like it's the concept I want to show you of what is astrobiology to understand. Okay. All right. So the ocean walls, it's just like it was shown in the video. I'll be talking about some important ocean walls that we know in our own solar system. So starting with Europa, we also call it as a gem of the Jovian system, because Europa has this amazing evidence on its surface that shows the life water underneath its crust. So if you see this Europa image overall on the left side of the screen, you can see there's like a lot of cracks, yeah, right? There's like lines everywhere. These cracks actually shows the surface of the Europa after it was constantly have a effect with water, and like the pressure, water pressure underneath this crust leads this crust to break into few pieces likewise. So this image on the middle actually shows the how it looked like with the images that we were taken from Cassini spacecraft back in 2000, I believe, 12 or 13, because right now Cassini is no longer working, but yeah, a few years ago we were able to capture these images. And then image towards my right shows the artistic view of how we see the ocean underneath the Europa's crust. So then of course you can see how crust is cracked because of the water pressure underneath, and then liquid ocean under the ice. All right, pretty cool, right? So and this image shows the jets of water on Enceladus. These jets are actually common in many ocean walls, so it's also included in Europa. Europa also has this. This is we call this plumes or ice plumes. These plumes occurred when the too much water pressure is inside the object, just kind of trying to break away that pressure by shooting its pressure outside the to the space basically. So what NASA is planning to do when we are trying to go to Europa through the Europa Clipper mission to understand the stuff in it, like the gases, and like understand the if the water is in fact is habitable enough to life to sustain. In order to do that, what NASA is planning to do with the Europa Clipper mission, to go through one of these plume, just shoot from this plume and get the spectrum data, so we can analyze and understand whether this water is in fact habitable enough for sustained life. So this plumes are very common in Enceladus. Enceladus is one of the moon of Saturn, and it's very icy. You can see if you take a picture, it's just like a white ice ball, and then this kind of shoots its energy to outside to this, like to the space, just through these plumes. And sometimes you could just imagine these plumes to be like a solar flares of sun. You know how sun, when sun has a lot of energy, just like shoot outside through the solar flares. And that's why we are when I was mentioning about earlier, like we need to have a magnetic field and atmosphere in order to be protected from solar winds. And these solar winds, it's what it just exactly look like in Enceladus. Like the plumes are just super tight and the energy is so high, so they're trying to reach outside the space just by shooting it like this, these plumes. So yeah, it's pretty cool. These plumes also, like we call it jets, water jets, like that. So the next slide. So this is like the another image of Enceladus, and just show you the artistic point of interior view. And it's an amazing place for us. Again, amazing place for us to see a life on Enceladus. Excuse me. So like, of course, we know there's an icy crust, and there's the ocean underneath the crust, a rocky core, like we see in other terrestrial planets, and then the possible hydrothermal vents, and the solar active jets underneath on the polar region. So the southern polar region, basically. So this image shows you the what we probably think is Enceladus is going to be interior version of it. So, and then there's a Titan. Titan is another moon of Saturn. So what's funny about Titan is Titan actually have a liquid ocean, just like our Earth, on its surface. So not like Europa and Enceladus, which has the ocean world underneath its crust. Titan has the ocean underneath its crust. Titan has the ocean on its surface, just like our Earth. That's the only moon that we can find water on its surface. But the thing about the Titan is, like, the reason why astrobiologists and NASA scientists does not believe that Titan will have able to have a life in it is because Titan is based on methane gas. So it is a little bit hard to explain, and probably we will not be able to find a life in it, even though there's an ocean, but it would be doubtable. There are ongoing research right now just to understand the Titan. And yeah, it's pretty cool. The Titan, if we can find a life in it, but I really doubt it, but we'll see. So it's very, so atmosphere is like 96% is nitrogen based and 4% is methane gas, and not just the gas on the atmosphere, but on the surface, it's just like methane is so common. And then surface is water ice coated in organics. The dunes is equatorial region. There's a hydrologic cycle, we believe, just like how Earth get water. We believe it's common in Titan as well. And then, of course, there are volcanoes, which is sort of like the poison volcanoes underneath on its surface. So it's pretty cool things to understand. Let's go to that. Okay, so when we are comparing Titan to Earth, we can see how similar in a ways Titan and our Earth, right? So there's a Titan cloud. Titan has a clouds just like our Earth has. Titan have lakes just like how our Earth have lakes. And there's a river channels, just very similar. And the dunes, sand dunes. So it's very similar. The moon and the planets are very similar. Just we doubt it, even it's possible to have a life in it, just because it's based on methane. So And then I'll go to the next one. Okay, so this is like the important one, that most excited slide that I was waiting to come, exoplanets. So one of the my second PhD thesis that I am actually planning to hopefully work on is detecting exoplanets. Detecting exoplanet is based on finding a planetary system that possibly similar to our Earth or our solar system in overall, and then see whether we can have a, we can argue whether it can have a life in it or not. But so exoplanet is, the definition is like the planets beyond our solar system, or is exoplanets. And there are several methods. I only put 4 here, but there are actually several methods of detecting exoplanets. The main 4 methods that we usually use, astrobiologists and also astrophysicists or astronomers overall, they use radial velocity method, the transit method, direct imaging methods, and microlensing methods. So the radial velocity method is like when the star is moved in a small ellipse, just like how Earth is moving around the sun. We use radial velocity method to identify whether the planet is orbiting their own parent star. If that's the case, there's a possibility for us to find an exoplanet likewise. So the transit method is like a planet passes between the star and the observer. So like, let's say I'm observing this planetary system, let's say 35 light years away from me, and I'm using my telescope. I'm looking towards the star, because star is the first thing I can identify because it's big. While I'm observing the sun or the star, I see an object moving in between me and the sun or the star. If that's the case, I can assume and I can actually identify, okay, this sun or this star has a planet that's moving around it. So this might be a planetary system body. So that's how the transit method works. So it's basically trying to figure out whether there's any kind of celestial object moving in between a star and the observer's point observing view. So, and there's a direct imaging method. This is basically mostly used one as well. What we do is we take a picture of a view that we assume that we can see majority of stars, and we try to zoom in and take more pictures, take the images in 360 angle, take images in 1-degree angle, and see, like, try to get the closer view likewise. So direct imaging is like mostly used by non-science, like citizen scientists. So citizen scientists means science educators or amateur astronomers who do not have access to big telescope or computer-based telescope. Once you study or understand the exoplanets in their own way, they just capture image and they try to identify it from there. And that's a microlensing method. Microlensing method is very similar to the transit method. So it's like basically what we do in the microlensing is like, so that if the light from a distant star is kind of, when this comes to Earth, but we can see it's kind of bend, that bend can let us to assume that there might have an object that in between us and the star that bends the light. Is that clear? You know, like how the light comes, if the light is coming towards me, and then but then there's an object kind of in between me and the light kind of bends and then comes towards me, right? So that bend shows me, proves me that there's a possibility of another object orbiting the star. So that's what microlensing method is. Very similar to the transit method. So this image, I just took it today morning. it was last updated in, if you can see all the way bottom right underneath the word exoplanets, it says November 25th, 2020. So it was yesterday. This was the 4,306 exoplanets are confirmed as exoplanet, and there are right now 5,668 candidates right now waiting for NASA astronomers to understand whether it's capable enough to predict to be a Earth-like planet or exoplanet. And there are planetary system, 3,196 planetary system NASA is observing. This information, I took it right now, like today morning, and it was last updated yesterday, which means right now, while I'm talking, astronomers and NASA astronomers actually looking forward for planetary bodies right now. Like it's always, this number always changing every day. If you check this number, like a week from now, you can see the confirmed planetary exoplanets. At least it's becoming a few. I think about 3 or 4 few going to be added towards this count, or maybe more than that. It's depend on the candidates that we have to work on. But every day it's changing. There's a number. So far we have confirmed 4,306 exoplanets, but we are looking forward for more than that. And this just by today. You can always check with the NASA exoplanet exploration website. You can see the updated amount. Every day it's changed like that. They update it daily. So it's pretty cool. So this is about the first exoplanet that we able to identify. So we call it 51 Pegasi b, and it was first announced in October 12th, 1995, and it was discovered by measuring the radial velocity of the host star. So you know, radial velocity is like the ellipse of the sun, of the star and the planet, right? And so what unusual about this planet is there's this giant gaseous planet very closely moving towards host star. So what is the other giant gaseous planet that we know in our solar system? Jupiter, right? But what funny is, like, just like Jupiter, this gaseous giant planet moved really closer to its host star or its parent star. So that's what got astronomers, okay, we might have evidence to show that gaseous planets does form near its host star. You know, in our case, in our solar system, we know that terrestrial planets, you know, Mercury, Venus, Earth, Mars, and then gaseous planet comes later afterwards, Jupiter, Saturn, Uranus, Neptune. So, but very strangely, this planetary system is very different. Like, this giant star is like right next to its host star. We don't know why. We don't know what caused it. There are more research has to be done. But this image shows you how artists were able to understand this is what it looked like when it's closer to the planet and the hot star. So, and we'll go from next. So as I mentioned about there are a few other methods of how we detect exoplanets, right? So radial velocity, the transit method, microlensing, imaging, time in variation, orbital brightness, modulation, and astrometry. And of them, actually, transit method is what we always use, mostly we use. So this image shows, I was able to take this from the Exoplanet Archive. You can see there are a lot of dots on the image that just shows you the methods that astronomers mostly use to detect exoplanets. I have a better approach. Hold on, let me show you this slide. Yeah, now you can see how astronomers were able to, from 1995 to up to now, this is how this green, red, blue line shows you the methods that we use to identify. So as you can see, transit method is the method that we mostly use, astronomers mostly use to detect exoplanets. So awesome. And this is like the periods, like the yearly wise. Honestly, exoplanet detection is the coolest thing you can ever come up with or do. Like, let's say you found a sun, like a star, like our sun, you get to name it. You know, you could come up with a cool name to make it. And then I was thinking, if I were to find a planet and a star system, I'm gonna come up with a Sinhala name for that, so everybody knows about our language. So it would be cool. But yeah, detecting exoplanets is one of my favorite subject in astrobiology, and I'm looking forward to do my PhD thesis. But hopefully, we'll see. And this is like important telescopes that we use to detect exoplanets, both space and ground-based telescopes. So that's a convection rotation planetary transit. We call it COROT. And then there's a wide angle search planet. We call it WASP. WASP. And there's a Hungarian-made automated telescope network. We call it HATNET. And there's a kilodegree extremely little telescope. We call it KELT. And of course, I hope you guys know the Kepler mission, which is like the most important astrobiology mission up to today. That was NASA launched back in 2009 and 2013. And then there's a transiting exoplanet survey satellite. We call it TEST. It's coming up soon. And then James Webb telescopes, we call it JWST. And it's coming up too. Those two satellites are one of my something that I'm looking forward to. Okay, so I want to talk about a little bit about the Kepler mission, which is because it is important for us to understand the mission overall. As you can see, there's an image shows on my left how the Kepler mission look like. So there were like two Kepler missions. There was a one Kepler 2009, but it was only able to work for about 3-4 years, and it kind of had a trouble towards 2013. And then we are planning to launch, or another Kepler K2. I don't know if they already launched it. They might have. I did not look for the K2. They might have, but K2 is the second. I think they already did back in 2013, the same time. I'm not sure, but K2 is the second mission of Kepler. But what important about Kepler is like it's like it gives us a lot of evidence and shows us images and the planetary bodies that we did not see before, and we were able to solve a lot of mysteries. And you'll see why. So this image shows where the Kepler was launched. It was launched towards the this constellation Cygnus, the Swan. We call it a swan like on the pond, swan. So the Cygnus, the Swan, is the constellation that Kepler was launched towards, because that constellation is right on the edge of Milky Way, and that it would allow us to get a good images of Kepler, good images of like the planetary bodies that we were not able to see from Earth. So the Kepler have the ability to stare in a 10 degree by 10 degree field of view for 3.5 years. It monitors the same set, like the same location, for thousands of stars. And it was by looking for the dimming of the stars due to the planet's transit. So they use the method of transit to understand the diminish of planetary body to capture that exoplanet system. So it's pretty cool. And you can see on my right, this image that just showed a bunch of squares. That's like the view angle of Kepler. This is how the Kepler took the images. So like that's just the view. it was not moved here or there, just moved right on that position. That's how it was able to take the images. So, pretty cool. So some information. So in January 2011, the Kepler team announced the very first discovery about a rocky planet with a radius of 1.r of radius of Earth. So it's a little bit bigger than Earth radius, but very much similar because it's a rocky planet, and it was announced in 2011. But this planetary body, we call it Kepler 10b. So when NASA named exoplanets, there's a way of they do it. They usually go with the mission name, which is Kepler, and they use they use the mission name, and then they use the amount of the planetary body that they were able to find, like the second planetary body they were able to find, and then they use with the ABCD and acronyms, like the alphabet. So this is like the first ever we found. That's a way of they do it. I'm not 100% sure. It's a little bit complicated the way they come up with the names, but I know they are always using the mission name first, and then the number or the day of the day or the number of how of the orbit or planetary object they were able to find. I want to double check on that, but yeah, it's a little bit complicated. And yeah, but this one is like the Kepler 10b is the first ever planetary body we able to find from Kepler's mission. And there's this one, the February 2011, scientists announced the Kepler found a very crowded and compact planetary system. So it's not like just a one star and a planet, it's just actual solar system. And then there's like a multiple planets surrounding it. We call this Kepler 11 system. Kepler 11 is but the thing about Kepler 11 is much closer to its planetary to the star. So our solar system, you can see in the image, is much bigger in size, but the whole Kepler 11 system can fit in between the size of in between the distance of our sun and the Venus orbit. So imagine how small it is, right? Kepler 11 system. So and then there's a same year and month, scientists announced, I mean, that's the same thing. They used this Kepler 11 system to name it like this. You can see B, C, D, E, F, G. That's like the way of the planetary body, like from the first planetary body, the last one. And Kepler, the 11 comes from the 2011, the year of they found it, I believe. So this shows you the how these planets orbit, and then you can see the yellow dots are planet B, and there's a red dot, planet C. Dark blue ones are planet D, and green is E, and so far so on. So it's pretty amazing how we're able to capture them and understand the flux from Kepler 11 system. So yeah. And then there's in same year, September, Kepler data confirmed the existence of a world with a double sunset, like one famously portrayed in film Star Wars. So that means they're like a two. It's not like a two suns. It's just a one sun, one star, but the planet that orbits the sun, that stars, is it's very small, and also orbits the sun very fast, and it's also revolve around itself very fast. So this occurs to us to have a, like, if I go to the western side, I see a sunset, but then I go back to the eastern side, I would see the sunset again, like that. So it's pretty cool. It's not a binary star system. It's not like there are no two stars, just one star. But yeah, this is like Kepler 16b. And then same year, December 2011, Kepler announced finding a planet outside the solar system that could have right temperature to support life. Now we are talking about actual formation of a life. And this was also very closer to our solar system too. And there is a habitable zone just like our Earth, and the same size, the habitable zone size is similar to our Earth. And the Kepler 22b is similar in size like our Earth, and it is like possible to have water in it, and we can assume it might have a life in it. But right now there are ongoing researches to understand whether we are capable enough to see that. So hopefully in few years we might have answers. But Kepler 22b is like the first ever planetary body that we were able to understand. Is like we also call it as an Earth-like planet, and possibly have a life in it, and it would be cool. So, and one more thing about Kepler's highlights. So in October 2013, the first Earth-sized planet was with the rocky position. So here, this one has the rocky composition. This is different. Like the one before in 2011 was, let me go back to the previous slide. It just looked like Earth, but it does. I didn't say it does inside. We cannot say whether it's rocky or whether it's gaseous. It just same size, same possibility of the similar gases most likely in it, and same size, and it looked like similar in a way. So it has the same similarities, but it's not confirmed to be whether it's gaseous or rocky. But in 2011, Kepler 78b able to identify as the same size first Earth-sized planet. So this one is very different from Earth, but very similar. Even with the diameter and the mass is very similar. So Kepler 78b surpassed the Kepler 22b, so which is amazing. This one has a rocky composition, just like us, has the mass a little bit more than Earth, but the radius is a little bit more than Earth. But what's different is like it's rocky. It's not really watery, or does not really confirm to have a water in it. But we in previous one we saw that, right? 22b has most likely water in it because it is orbiting a habitable zone. It's inside the habitable zone. Size is similar too, but here this one is very similar with everything, but it's just not in the habitable zone. Neither it can confirm to have an ocean or water in it. So that's like the differences between those two planetary bodies. So the TRAPPIST-1 system. So this one is not found by Kepler. Right now, Kepler does study it, but it was originally was found by Transiting Planetary and Planetesimale Small Telescope that was located in Chile. This system was found in, I believe, 2015, not too long ago. And this planetary body consists with planets B, C, D, E, F, G, H, and you can see how it's similar. And you can see planet D and planet E very similar to look like our Earth, right? And you can compare their orbital period, distance of the stars, planet radius, planet mass, planet density, and surface gravity with our Earth, and see how similar or different they are. But you can see these are like the TRAPPIST-1 system is like the first ever planetary system that we found with multiple Earth-like planets. That's what unique about TRAPPIST-1 system. And right now there are a lot of ongoing researches happening to understand whether to understand and study more about the TRAPPIST-1 system. So even though it was initially found by transiting planets and planetesimale small telescope in Chile, it was also supported by a few other telescopes that was located in Chile, and they all are ground-based telescopes, and also some planetary observatories that was located in Hawaii, in Mauna Kea. So yeah, but it was initially found by the TRAPPIST telescope. So okay, so something very cool and similar. Are we looking for SETI? Search for extraterrestrial intelligence? Yes, we are. We are looking for it. We've been looking for it for a long time, and we still are looking for it. So that's the Voyager Golden Records. If you see the image on my left bottom, that gold plate, it was actually, I captured this image when I was visiting NASA JPL. They had same one, but like, you know, just another copy of it, copy of original one. I took this image, shows you the record of our Earth. To find our Earth, it has the image of location of our Earth on in the universe, and have some sound, like recordings in several languages. It's include our own language, Sinhala, and Hindi, English. Of course, there are several languages our recorded, but how we say hi or hello, and it was installed in this record, golden record. And this was first, I think, no, it was maybe after that. Carl Sagan is one of the first ever pioneer astrobiologist. He did a separate golden record. I think it could be the same one, but he came up with the idea. He actually drew the images of a man and a woman in it. So I'm not sure whether it's the same one as this one. I think it's two separate ones. Could be the same one, but yeah. If you're interested, you can of course research about it. But that Voyager Golden Records, it was installed in both Voyager 1 and Voyager 2. And then that's a acrobio message, or we call it in interstellar radio message. It's carrying the basic information about humans and to globular cluster M13. So you wonder why it's M13, right? I did this research about M13 globular star cluster a few years ago. I was actually imaging it, like I had to stay up late. Oh my God, it was like the worst time to do research, just because it's so cold. Winter in New York is so bad. And it was my first ever independent research study I did. And I had to stay late in my observatory at my university, and me and my partner, we took images, and we had to put on the several registacks, which is one of the photo like a image processor, and we put several other analyzing Photoshops, and then we kept doing it multiple times. I don't know if I still have the image. I might have it. I should put it in my Facebook or something so you guys can see. That's my first ever image processing of M13 globular star cluster. And what is interesting about this thing is, oh, actually I found it. I don't know if you can see this. Do you see this, like a small cluster? I know it's not probably clear.
Yes,
right?
sir, we see a cluster.
Okay, good. All right, great. So this is the image of globular star cluster M13. This is the image that I was processing. I was able to take and photograph it from telescope, and then I put on several Photoshops, not Photoshop, actually the image processors like Registrax, and it's not clear. It has a lot of noise in it, but we had to put different filters in it, and we process the image likewise. But what's important about M13 is one of the star cluster that is old. So any globular star clusters that we can find in the universe are what we believe is first created after the universe was created. So when we look back in the time, globular star clusters are relatively very old than any other celestial object. And globular star clusters are a bunch of stars that are closer to each other as just staying there. And then we believe if there's a globular star cluster, there might have advanced civilization, might be from one of those stars in that cluster. So there's a open star clusters, which is much younger version, but this is a different topic. But globular star cluster M13 is something that we were very interested in. Okay, I can see somebody's annotating, so I'm going to control it. Okay, hold on. Okay, all right. So so that's the Akriba message, and then there's a wow signal. The wow signal is in 1977. It was directed by astronomer Jerry Heyman. He was doing his research at the Ohio State University Big Ear Radio Telescope, and it is a radio signal that detect at the time was pointed at a group of stars called T Sagittarius. It belongs to the constellation Sagittarius, and then there was a bunch of metric numbers that was just coming up, and he used these numbers and compare with the alphabet order and came up with the word "whoa." So we don't know whether it's a coincidence or whether it's someone actually saying us a message in, oh, look at that Earth, whoa. So we don't know that, but yeah, that's the pretty cool thing about okay. So do you believe in aliens? I want one of you to unmute and tell me the answer. Come on. You can unmute yourself and tell me whether you believe in aliens or not. Just make a guess. You could be right or wrong. It could be right or wrong.
Most of the participants do believe.
You believe. Nice. Because I do too. I do too. I believe it. And what's funny is, like, I took my astrobiology class and my professor didn't, he told me, Malmi, I'm going to answer your question. That was my first question. I'm like, I asked him, can you tell me whether you believe aliens or not? And he's like, Malmi, I'm going to tell you the answer at the end of the semester. So I was so excited. I took this class. I showed up to the class on time. I even tutored my friends at the time before I actually became a tutor. And I was very passionate to identify the answer, because it's like he going to give me the answers, right? And this man had the audacity to tell me that he did not believe in aliens. And that was in a minute I was like, I really wish you are not a professor, just my friend, that I could punch you right there. Because how would you say, when you're an astrobiologist of your own self, like, how would you say that you don't believe in aliens? And he said, there might not be aliens. We might be alienate other planets, like what we're going to do to Mars. In several years, we might be, the human civilization could be treated as gods to other plant bodies that is right now developing or creating like that. And he came up with this theory and stuff, but we had a huge argument. But he was one of amazing professors in my undergraduate, and he was my mentor as well. But yeah, he does not believe. But I told him, I'm gonna prove to you in my life, and we're gonna have this argument again. But it was funny. Yeah, so I do believe in aliens, and this me photograph with alien, not a real alien, but it was one of the lecture I had to do one of the telescope society, Long Island Astronomical Society. It was a long time ago, but yeah, that will be the end of the talk, and I really hope you enjoyed and you learned something very interesting and you learned something from me. And thank you once again.
Well, we should thank you, Ms. Malmi. The session was indeed inspiring. Like, how do I say that? Let me put it this way, okay? Someone like who isn't that into biology, but like after this session, I feel like I should start over again. Hope you get the idea. So, actually, there are Namrod,
Mhm.
so shall we take a look into it?
Sure. Yes.
Okay, so the first question, it's basically referred with aliens and stuff. So why do we use human beings as a reference for finding life on other planets?
So why do we use
Human beings. So
human beings as
I
okay,
I guess that's like based on the parameters that we use, oxygen, water, and that stuff.
right? So there are several ways to explain. So the way we use why we use human beings. Actually, we not only human beings, we use our Earth to understand the life in other planets because Earth is what we are came from, what we born. This is like our mother and all, right? So when we know the formation of life in Earth, we can use the same method of formation of a planet outside the Earth, or the life origin of the life in another planet, because we all belong into same universe, right? So if the universe is similar, the images we take, like the sun, the stars that we photograph from outer solar system, if they are very similar to what we see, and then is there's a higher possibility of a formation of a life in another planet. It's very similar to us. But if you're talking about the look or the physical reference of a human beings, it is doubtable if the atmosphere that planet is based on atmosphere of our planet. um, we might able to find a human, or not human, alien life similar to our body or our physical appearance. But if the other planet has a different atmosphere that we don't know and still able to sustain a life, let's say we are carbon based life, whereas they are silicon based life, which is possible to find a silicon based life. They might have a different physical appearance, we don't know. But most of the time scientists, when they were looking for a life outside the Earth, they're looking for a carbon based life, um, and also silicon based life. But anything other than that, it is doubtable. But physical wise, we can really say that the life outside the Earth, with the alien life like our physical appearance, could be a green man with the 3 fingers. We can really say that. But someone like astrobiologists, they, what they do, they're looking for a microbacterial life. So as I mentioned on like about Europa, and like what we are looking for a uh, microbial life underneath Europa's crust, on its ocean, liquid ocean. We are looking for microbacterial life, so microbial life or microbacterial life. But there will be another planets with the already evolution happened, and now microbacterial life is no longer there, but they have to have advanced civilization like us. It's doubtable, we don't know, we haven't find a alien with a physical appearance like us, but we can predict that in our own solar system we can find a microbacterial life. So I hope it's answered.
Yes. So I hope the question is answered for the person who asked the question. The next question that we have is,
Okay, we have a participant who would like to ask a question too.
okay, we'll give the chance to him.
So, Iresha, here you go. Iresha, you can unmute yourself. Yeah.
Um, is anyone get a signal from aliens or see them?
Sorry,
Say
Iresha, can you repeat the question, please?
Uh, is any scientists have see aliens or have a signal from the aliens?
yeah, so we we are not officially haven't seen a alien uh, life yet. we assuming, because there are 100 of possibilities, but we haven't seen. But the radio signals, there was an article about radio signals recently too, it's very doubtable. We don't know whether it's a radio signal coming from directly from a planet, from alien planet, or whether it's just a death of a star and that just kind of whoops around us and just go through our Earth, just gives us the radio signals. Likewise, that don't know. But so far as long as I know, we haven't seen an alien, or neither we have seen a microbial alien. So
Thank you.
yeah.
And we do have another question from Jacob S. He wants to know your opinion on the parallel universe concept.
Oh, I was waiting for someone to come up with that question.
So well, thank you, Jacob S. Then.
Okay, so first of all, I do study astrophysics, but I am not too deep side on it. Like my best friend, he is like my one of the best colleague. He's like all about astrophysics, cosmology, as such as like blah blah blah. But parallel universes is just a theory. We don't know it's right or wrong, but what I know is like parallel universe is like there's another universe just like our Earth, right next to us, or maybe on the same boundary. So maybe I'll draw this image so you can see. So Earth 1, Earth 2. Can you see this? Yeah.
Yes,
So
yes.
Earth 1, Earth 2. Let's imagine. Hold on, I'm going to need a different marker. Okay. Imagine these two planetary bodies are lined up. If I bend this book, it's located in the same place, same position. Okay. But I'm just drawing it like this to illustrate it. But Earth 1 is us, our planet. This is where me, you, and Earth 2 is where is the other people who live in Earth 2. So like, let's say your doppelganger. So my doppelganger could be someone who study the same subject but but going for different field. It could be like that. They might have a same life story like me, but could be different in other ways. It's like there are several theories for this. But what I'm saying, these two planets, Earth 1 and Earth 2, they're located in the same place, same boundary, in the same in the universe, but it's still separated by two universes. Earth 1 and Earth 2, we cannot see each other because Earth is vibrating in these Earths are vibrating in a different frequencies, like shaking like this, and because if this frequencies is too tied up, we cannot see each other. So there are Earth 1, Earth 2 in the same location. We are in our own universes, still two different universes, but we are the same location. We cannot see each other because we are vibrating in a different frequencies. And only way to break this barrier of frequency for us to travel from Earth 1 to Earth 2 is running really faster than speed of a light. So that's the theory of parallel universes, but it's a hypothetical theory. We don't know if it's true or not. It might be not, but it would be cool if we can find. But I do want to believe it because it's cool to imagine there's another somebody like me, or there's another somebody like let's say Neil Armstrong or something. So yeah, but that's the theory of parallel universes, and I hope I answered the question.
Yes, okay, and we do have some other questions too. And on the line we have Sumit Muralidharan asking on about the expansion of the universe. What is exactly universe expanding into? What's there to expand?
Awesome. Good question. So when there are several theories about expanding the universe. So it's just not, when we are thinking about expanding, some people believe, oh, when we are expanding, that means we are stretching out. The universe is stretching out from different locations. So like, let's say this tissue is the our universe, and now it's expanding, and it's expanding for a different location, and it's move around. But when you expand something, what happens? It stretches and it breaks, right? And then it still keep going to expand. But one of the theory that astronomers came is like this universe which stretch, the end of the universe would be it coming back onto its position and crunch its own and vanish. That's like the another theory of how the universe expand, and just, it's expand and then it kind of stretch on its own. It could go on its own way, or if it stretch enough, and then it kind of crunch back on its own and just vanish like this. So that's like one of the yeah, it's like one of the theory of astronomers. But others believe the expansion is our universe is just moving towards somewhere, or the edge or something like that. Like, we know that our solar system, like, we are revolving around the sun, right? Sun is revolving around our solar system, including our sun, of course, revolving around our galaxy. And our galaxy is revolving around the black hole, the giant black hole on the middle. And our galaxy is also revolving around the universe likewise, in a cluster of other galaxies. So it's just like that. What we don't know is, we don't know where we're going. It's just funny to understand. We don't know where we're going. We don't even know what is the middle of the universe. If somebody asks me, Malmi, tell me where is the middle of the universe, I don't know. Nobody knows. We don't know where the universe originated or where the universe is going. We don't even know where it's going. We just know the theories why. There are several theories, like the expansion could be we are just moving towards different directions. Like, it's not like a significant movements. It's just like the little, very little movements. So we can't even feel it or see it. As another theory, I believe, so that there's a crunch and there's an expansion and there's a expansion. Oh, there's a some people believe this. This is like a funny theory. The universe, in the middle of the universe is a giant black hole, and we are moving towards this black hole. And once we go towards the black hole, we're just gonna wooz around it, our galaxy just getting it, and then we're gonna disappear. That's something, but that's not real. I don't even think it's a real thing. But there are several theories, but most likely accepted one, it could be the crunch, that we stretch ourselves and then come back to itself, and then we expand again. That's when the Big Bang happened. So it happens like that several times. So it's just not one time. Or it could be we stretch and we kind of separate ourselves. So we will go different directions. So there are several theories. So I hope it answered. Yeah.
Yes, and we are getting more and more questions. And there's one question from Mr. Randimal Vijay. He wants to know about the SETI at Home software app contribution and ISS Live app. If you know.
Say it again. I'm sorry. SETI?
He wants to SETI at Home, the software app, and the ISS Live app. He wants to know more about it.
I'm not familiar with SETI app. ISS Live is the International Space Station Live app. If that's the one you call, I do not have that app downloaded, so I'm not sure their functions. But if you are even the software, I'm not familiar with it. I will look forward. If you could email me, my email address, I will send in the chat box. You can email it to me, your question. I will take a look around and see, but I'm honestly not sure about those app or the software itself. But this is my email. Okay, you can send it to me.
We also have 2 questions from Imasha and Felon. They want to know how to become an astrobiologist, and maybe they want to know about your path so that it would be a motivation for everyone.
Awesome. Thank you for that question. That's a really good question as well. Well, if I tell you about my path, I'm sort of like everywhere. Well, of course, when I was coming, okay, let's start with how to become astrobiologist. So in order to become astrobiologist, you need to have a bachelor degree in a physical science, which means whether it's a geology or astronomy or biology, chemistry are mostly required as a subject for your undergraduate degree, which is the bachelor's. And you have the chance to, in schools in US, you have a chance to skip your master's and go straight for your PhD, which is what I'm doing. Like I was going to school for a very long time. Usually undergraduate is 4 years, but I've been in an undergraduate for 6 years. That because I have 2 degrees separately from my associate, and then another 3 years of my current university. And that because I'm skipping my master's. Because I'm skipping my master's, all my classes that I've been taking for the last 2 years are graduate courses or courses that students who go in for master's degree taking. So I have the chance to avoid the master's degree just by taking classes for the last 2 years of my undergraduate and just go straight for my PhD. So my PhD usually in US is last from 6 to 7 years, could be 5 depending on your research. Mine probably going to be 5 years because I've already taken all the classes that I needed. I'm going straight for my research. So you need to take your undergraduate in physical science, and if you're planning to go for your master's, you could I don't think astrobiology is offered as an undergraduate degree in any schools as far as I know. You can get your master's degree in astrobiology, and then from there you can apply for your PhD in astrobiology as well. So once you get a PhD, you are sort of considered as an official astrobiologist, and you can work for universities and get funded to do researches through NASA or other space agencies. And if you're going to some other universities outside Sri Lanka or not, it's not in US, there are amazing astrobiology programs in many nations around the world. The closest one for us is India, has an amazing astrobiology program. India has an amazing astrobiology program, and also there Australia. I have one of my friend who actually interned at NASA JPL. She's a pioneer astrobiologist right now in Australia. Australia just got astrobiology as a subject in its academic system for their master's and PhD programs, and she's one of the pioneers in astrobiologists in Australia. So if any of you wants to become astrobiologist and looking forward to go somewhere, the easiest way for you to I would recommend is go to Australia for an undergraduate or your master degree. They will offer you more possibilities because they're very new. Their astrobiology program is very new. So when something is very new, that means you have a lot of possibilities. So you should definitely try go somewhere in Australia. And if you are looking for settling down Australia, once you have a degree from Australian University, you can actually get for your permanent resident as well. So that's something you should look for. But there are other universities around the world you can look for astrobiology programs. But definitely get your undergraduate in physical sciences. Even it could be a environmental science, but mostly if it's biology, that would be great. Okay.
Yes, and I guess this would be the last question for the day. And it's really interesting, Mr. Mr. Dinadar Senuru wants to know, and his question is, if we talk about aliens, what about Fermi paradox? And he also wants to know about the Roswell incident, whether it's true or not.
Say it again, the paradox part.
He wants to know about Fermi paradox and the Roswell incident.
Okay. I'm not familiar with Fermi paradox or Roswell incident. I will be honest. I've heard about it. I've not put my interest to understand it. Let me research about it, and I'll get back to you. You can email me about the question. I don't know honestly about them. For the fact, I don't believe in paradoxes or neither incidents as long as they are not unscientifically proven, because to me as a scientist or scientist to become, I believe in facts is much important than the theology or the hypothesis or the faith that you have on something that you believe in, whether it's your religion. So facts is something that any as scientist look forward for. So if something is the paradox is explained by scientifically proven facts, I would definitely research about it. But yeah, I'm not so sure about that incident or the paradox. Okay.
All right, so then that concludes the Q&A session for now. It's because of the time concerns. I'm really sorry, guys. It was really wonderful having your questions here.
Thank you, everyone. You guys also send me an email. So I do have my Facebook page, which is much easier to contact me from. You can Google. You can also Google my name, and the Facebook page would just come up. So you can access and ask me the questions if you have.
So guys who have more questions, then you have the way to get the answer, right? So with that, we shall now invite Mr. Pasidu Hatrasinghe, who is the media division official of SEDS SLTC and also the project manager of this session, to give the thank you speech. Mr. Pasidu?
Yes, thank you. Okay.
You're welcome.
Our guest speaker, Ms. Malmi Pasandi, for gracing this occasion despite your busy schedule. It is much appreciated. I would also like, I would also like give my heartfelt thank all the participants for being here with us. Last but certainly not least, thank all the board members of SEDS SLTC for being helping this event possible and success. So thank you guys and good night.
All right. Thank you, everyone. I appreciate for coming in.
So yeah, with that, we shall now conclude this session. And Ms. Malmi, thank you once again. That was a brilliant session, and we are looking forward to have another session with you if you're okay.
Yes.
So
yes.
Thank you, participants, and thank you very much.
Okay, everyone, please be careful in with the pandemic going on, and those who are interested, you can contact me anytime. And thank you once again, SEDS. You guys are amazing. I'm so glad to know that young Sri Lankan students are now very involved with astronomy. Back in the days when I was there, I was very few amount, but I'm very glad that you are a part of SEDS, and keep up with the good work. And thank you once again for inviting me. Everyone, stay safe.
Yeah, you too. Bye. Have a good day.
Bye.